Hello, my name is Eric Sondy, and I'm the Product Manager for SoC Design Solutions in the Development Solutions Group here at ARM. I'm happy to be here today with my colleague Holger Ketting at Synopsys to introduce to you a new solution we have collaboratively developed to enable our mutual customers to explore and optimize ARM-based SoC architecture in the data center using performance models. Today, we will start by sharing with you some of the trends we have observed in the data center to give you some context on why we created this solution in the first place. We will then briefly cover ARM's Neoverse IP portfolio employed by SoC architects and hardware developers in this segment, and also dive into some of the design challenges that they are facing. I will then introduce the new ARM performance models technology we are providing as a key part of the solution to address the challenges described. Then I'll hand it over to Holger to talk about the virtual prototyping methodology and how it takes advantage of performance models. Holger will also provide a very compelling demonstration and application of this methodology on a real-world use case for benchmarking the ARM-based server. There are three trends we have observed relating to compute in the data center. The first is a trend towards an ARM-based server. These are powerful, high-performance compute nodes for enterprise computing and cloud CPUs. The second trend is that these servers are being designed by cloud service providers, with the most recent example being the 64-bit Neoverse-powered Graviton2, custom-built by AWS for AWS. And we expect that there will be many more examples to come in the future from several other cloud service providers designing with ARM. The third trend that we observe is that these cloud service providers are optimizing their server designs for their workloads, with cloud workloads requiring dedicated cores per thread and driving the core count higher for the server class SoC. Neoverse N2 is a highly scalable CPU and provides our partners latitude in attacking the cloud-to-edge spectrum. We see N2 addressing many problem spaces, from scale-out cloud down to edge compute. The N2 efficiency profile provides a lot of design freedom. Partners can build low core count, low frequency, power envelope optimized systems. At the same time, they can take the same N2 core and build high core count, high frequency, large memory bandwidth monsters for the data center. And it's in the data center where we see the largest ARM-based servers, where N2 scales very well to high core counts. The efficiency profile allows partners to fit more threads per socket. Along with our Neoverse cores, we offer partners key resources needed to rapidly kick off designs. For Neoverse N2, we offer the Neoverse N2 reference design along with the CPU. In addition to providing architectural guidance and best practices at the system level, our Neoverse N2 reference design allows our partners to left-shift software development and boot an OS on day one. Now, starting from the N2 reference design, there are two key challenges architects face when designing for the data center. The first is scaling their SoC architecture for their workload, and that requires workload modeling of the many CPUs in the system, along with assessing the behavior and the performance of those workloads on the system architecture. That involves analyzing the impacts of memory and I/O subsystems, as well as analyzing the effects of varying core count on the coherent mesh interconnect. The second challenge is balancing power while scaling performance, and this is where performance-defined power management, or PDP, enables the dynamic scaling of the microarchitecture to maximize efficiency, where not every workload requires the maximum configuration to perform optimally. Now, at the heart of the SoC is ARM's Coherent Mesh Network, or CMN IP, and configuring and optimizing this central design element is the key for meeting these two challenges. ARM's highly scalable, multi-chip optimized, PCIe Gen 5 ready coherent mesh network is the heart of the Neoverse N2 reference design, enabling key features from ARM v9 architecture, like memory tagging extensions or MTE. Tuning the highly configurable mesh topology and distributed system cache for the desired core count and workloads is a primary objective of the SoC architect. As you can see here, there are many parameters that define the highly scalable interconnect. The topology is capable of expanding up to a 12 by 12 mesh size, enabling up to 128 coherent clusters of ARMv8 or ARMv9 CPUs or accelerators, over 80 I/O nodes for over 160 AXI and ACE interfaces, and up to 40 dual-channel memory controllers. There are also a number of microarchitectural features that can be defined to trade off power, performance, and area. and this includes data widths, coherency domains, system-level cache partitions, and much more. For such a sophisticated and fundamental SoC component, our hardware designers need a flexible design tool to rapidly model the mesh topology and understand the behavior and performance of potential configuration parameters. For that reason, we are introducing to you today ARM CMN performance models. These are fast, accurate, flexible models that enable SoC architects to easily specify their mesh layout and also configure and iteratively reconfigure the performance-critical features of the CMN microarchitecture at runtime. ARM performance models also have a range of features that enable deep performance analysis, including validated AMBA interfaces, inspection and performance measurement of traffic through the mesh, TRM-defined performance counters, as well as additional performance-critical microarchitectural statistics. And to take advantage of this model and its capabilities, we've collaborated with Synopsys to integrate this model into a solution and methodology that allows SoC architects to easily run performance experiments and studies across a range of topologies and CMN definitions in the context of their desired workloads. With that, I'll hand it over to Holger to introduce this new solution and methodology, as well as to provide a demonstration of its application to a real-world ARM server-based case study. Over to you, Holger.
Thanks, Eric. In my part, I will first explain the flow for building a virtual prototype for early architecture analysis. After that, we can look at some demos, which show the flow as applied to an ARM server case study. The traditional design flow for designing an SoC architecture is to use spreadsheets for some high-level analytical modeling and to come up with high-level specifications. The first time you can really measure the key performance indicators for power and performance is when you run the software image and the hardware RTL and emulator or FPGA prototype. These are great tools for hardware-software co-verification and pre-silicon power and performance analysis, but for the analysis and architecture perspective, this comes pretty late in the design cycle. Also, at this point in time, the turnaround time is too long for architecture exploration and optimization. Therefore, we propose to shift left and analyze power and performance using architecture simulation with transaction-level models. This enables hardware-software exploration and optimization based on full use cases. The transaction-level models have sufficient accuracy to take design decisions, and they give good analysis feasibility and fast turnaround times. And even mixing the two approaches for validation purposes later in the design cycle is possible. This slide first explains the flow of Platform Architect, our virtual prototyping tool for architecture design. The first step is to build an application workload model. The application task can be executed to check the correct execution and get an initial understanding of computational intensity and the available thread level parallelism. For server benchmark applications, the workload model is generated from software execution traces. I will explain this more in detail in the coming slides. The next step is to build a model of the hardware platform using the components of the Platform Architect model library. This model library also includes the new ARM performance model of the Coherent Mesh Network, or CMN. The application workload model can then be mapped to the processing resources of the platform. The resulting system performance model simulates the execution of the workload under the constraints of the available hardware resources. The root cause analysis shows many performance metrics like, for example, application latency, utilization of processing elements, bus contention, memory bandwidth, and many more. The power consumption per component can be specified as a UPF power model overlay. This way you can analyze system-level power, energy, and performance based on the actual application use cases. Once the SoC or performance model is validated, it can be used for systematic design space exploration. You can define parameter sweeps, and Platform Architect manages the parallel execution of the scenarios. The extracted power and performance metrics can be analyzed inside Platform Architect or fed into other analysis or collaboration frameworks. Now, as promised, let's look into the generation of workload models in more detail. As a first step, you can generate synthetic traffic models to analyze the response of the hardware platform to well-defined traffic patterns. These synthetic traffic models are essential for validation and testing, but not very realistic. So what we have developed is a flow to generate more representative workload models of benchmark applications. The idea is to generate the workload models from software execution traces. The starting point is to run the benchmark application on a virtual platform for software development. For typical ARM server reference platforms like Neoverse E1, V1, N1, or N2, these are readily available as fixed virtual platforms from ARM or extensible virtual platforms from Synopsys. While running the benchmark software, the virtual platform tools from Synopsys record a range of traces. The Linux ftrace is built into the Linux kernel and records the OS level and thread level activity. A more detailed function trace captures the function call trace or call stack of the benchmark. What we also record is the address sequence of the instruction fetches and data memory accesses. These traces are then translated into a hierarchical workload model which represents the processing and communication requirements of the benchmark application. At the highest level, the Linux ftrace is converted into a thread-level task graph which models the dependencies between the benchmark threads. The typical structure for benchmark applications is an initial main thread and a number of parallel worker threads. The function trace is converted into a function-level task graph. Here, each task represents a function, and the connection model the call stack, that is, one function calling another. The address sequence is converted into a transaction-level trace file that models the level 1 cache misses, or in other words, the level 2 cache requests. This way, each task produces the transaction sequence to the coherent level 2 cache, as in the original benchmark software. The actual processing is abstracted. We only model the number of cycles between two consecutive transactions. This generated workload model is then executed on the transaction level model of the hardware platform. In case of our ARM server platform, the dynamic shared units are modeled as CPU core and a configurable architecture model of the coherent level 2 cache. The workload model is executed on the CPU core and generates the level 2 cache requests. Depending on the address sequence, the coherent L2 cache returns immediately in case of a cache hit or generates CHI requests in case of a cache miss. At the top level, all the DSUs are connected to the performance model of the ARM coherent mesh network. Depending on the specific configuration, this accurately models the processing of the L2 cache requests. The CMN model sends Snoop requests to the other coherent caches or forwards the requests to the performance models of the CHI DDR controllers. Together, the generated workload model and the transaction level model of the hardware platform represents an accurate performance model of the server SoC running a benchmark application. For other application domains, Platform Architect provides further flows for the generation of workload models. For example, Platform Architect comes with an operator library for deep neural networks and an import utility for neural network graphs from TensorFlow or ONNX descriptions. The imported task graph represents the processing and communication requirements of the neural network running on a deep learning accelerator. Of course, in a heterogeneous platform, different types of workloads can be combined into a system-level workload model. But now enough for the theory. Let's look how we did this in a case study using the Google Multichase benchmark on a CMN 700-centered Neoverse N2 reference design. Here you see Platform Architect's Platform Creator GUI, where we have assembled a base architecture for CMN 700 and memory subsystem performance analysis and optimization. Central element is the CMN 700 cache coherent interconnect. The model used in Platform Architect is the TLM performance model that Eric also described before. As you see here, the list of configurable parameters of the CMN 700 performance model is considerable and allows for efficient parameter configuration sweeps for architectural exploration. On top of that, the Platform Architect integration provides additional analysis capabilities that you will see later in this case study. On the right-hand side, you see the 8 DDR5 memory controllers that we use for this base architecture, all configured to use CHI as interface to the CMN 700 interconnect. On the left-hand side, you see the 16 DSUs, dynamic shared units, that are interfaced to the interconnect, also using CHI as protocol. These DSUs are also part of the workload model that we use to analyze and optimize the performance of the entire architecture. For any kind of architecture exploration, it is crucial that the dominant and critical use cases are reflected by the workload models used during the optimization. Now, for a server type of architecture, that is easier said than done, as there's a vast number of different applications running on a server, and you cannot even assume the mix of applications to remain the same over time. You could almost come to the conclusion that you cannot assume anything specific on the workloads running on a server, but that's also not true. There are a row of very inspiring publications on that matter. For example, a paper from Google and Harvard University on profiling a warehouse-scale computer, where they presented a detailed microarchitectural analysis of live data center jobs, measured on more than 20,000 machines, Google machines, over a 3-year period of time, comprising thousands of different applications. The authors identify common building blocks in the lower levels of the software stack that can be optimized for, and also point out the opportunities of optimizations of the cache hierarchy. And this is exactly what we do in this case study. And there are benchmark programs, some also publicly available, such as the multi-chase suite from Google, that can also be used to create workload models with data center typical characteristics. The methodology to create workload models for Platform Architect is to first run the benchmark programs on a Neoverse N2 system and record traces. For example, function calls, context switches, OS level dependencies, as well as memory access patterns. In our case study, we have used a Virtualizer Development Kit, or VDK, for this, as besides its ease of use, it offers unique introspection and analysis capabilities to get the required trace data. So after booting Linux on the VDK, we executed the benchmarks and recorded the required traces, the function calls, context switches, OS level dependencies, and memory access patterns. The VDK trace data is then used by Platform Architect's task graph generator to generate task graphs representing the function call hierarchy, activations and call sequences, and memory access patterns of the different functions and threads. Here you can see a generated task graph reflecting the same functional call graph that you have seen in the function traces shown for the software execution on the VDK. Some of the task graphs generated are rather complex, since many service routines were called during the trace captures. Others are more simple, and the benchmark program or the benchmark worker threads are more dominant. Each of the threads replay a memory access trace file that reflects the memory access patterns during the recording interval. With the benchmark workload models created by Platform Architect's task graph generator that are now mapped to the DSU models of the CMN 700 based architecture, you can now run simulations with introspection and analysis instrumentation. The typical first step at this stage is to start a simulation in performance debug mode. Record performance metrics for all major elements in your design, and analyze the performance of the architecture and, most important, of the key performance indicators, or KPIs. In our case, these are the achievable throughput at the DSU ports, this is what you see in chart number 1, and the latency of the memory accesses, which is what you see in chart number 2. Both metrics have a direct impact on the time it takes to execute our benchmarks. You see that initially the throughput is a bit lower and the latency is high. This is expected behavior initially as the caches are cold. To validate that, we can analyze the performance metrics for the caches and see indeed that initially the cache misses, shown in chart number 3, and the snoop requests, shown in chart number 4, are higher. To further check the expected behavior, we can also look at the DDR5 memory data channel utilization in chart number 5, which is also initially high. For every cache miss that there is a request to the memory, and after the caches are filled or warmed up, the requests to main memory decrease as well. To validate that the memory access patterns of the benchmark application are reasonable, you can take a look at the transaction address traces for all benchmark programs in the chart on the bottom. You see clearly that there are different regions of high and low memory being accessed from the software programs. You can get a better picture of the address distribution if you open the address trace charts for a single DSU and zoom into the area where you do not have both accesses to high and low memory regions. Here you can see clearly the irregular address patterns of the benchmark program that would be difficult to guess by artificially generated synthetic traffic. The CMN700 performance model from ARM also provides internal performance counters, for example for link utilization of the mesh network. Looking just at an ASCII dump can be mind-boggling though, so the model also comes with a graphic utility that maps the link utilization numbers for the different CHI channels, for example Snoop, Request, Response or Data channel, to the graphic representation of the current CMN700 configuration. If you want to validate or debug in detail which CHI transactions are being sent from the DSU to the mesh network or from the mesh network to the attached memory controllers, you can use the TLM port traces that show you each and every transaction. As you see here, for a larger simulation time, you're just able to identify times and areas of the activity. But zooming in on time, you can identify the single transactions, and for each of them get detailed information on its type, status, and even get related other transactions highlighted in the trace charts, which makes it easier to read the traces. After you have validated the overall platform behavior, and most likely have fixed some initial issues with the configuration of the models, you can go over to systematic exploration of the design space. For example, you can create parameter sweeps for the parameters of the CMN700, such as the system-level cache sizes or the size of the Snoop directories. So you can find the optimum configuration for the CMN700 as well as for the memory subsystems. For the specified combinations, you can run one scenario each, and the scenarios can be all launched in parallel to shorten the time to results. And this already brings us to the end of our presentation. We have highlighted some of the trends and challenges for data center SoCs and how a scalable and flexible ARM Neoverse N2 and CMN700 based architecture can be tailored to address these challenges. You have heard and seen in a case study how our common ARM and Synopsys solution using the CMN700 performance model in a virtual prototype can help you to shift left the architecture definition phase. This always has to start with one of the key ingredients to meaningful optimization, that is, with suited workload creation, and ending with exploring different configurations of the coherent interconnect and the memory subsystems. We would like to thank you for your time and attendance and are looking forward to hearing from you.